Hey everyone, welcome back for another session during the Global AI on Virtual Tour. And with me today is Amy. She's back from a break. I hope you had a good break.
I did. I did. No, it's lovely weather here in the UK today, so I did get a little bit of time outside, which was a treat.
Oh, that's so lovely. Yeah, it's great weather as well in the Netherlands. How is it in Sweden, Alan?
It's nice and sunny today, yeah.
Oh, pretty good. Global warming doing it for us.
Mm.
Okay. So, as a speaker, we have Alan Smith. He's currently living in Sweden. He does a lot of stuff around cloud computing, but in his spare time, he likes to beat the computer at StarCraft 2, or maybe use the computer to beat the computer. It's a sort of an inception thing. So, Alan, can you tell us a little bit about the topic that you're going to talk about?
Yeah. I got motivated by watching a guy called Centdex who does loads of Python and AI videos on YouTube, and he'd looked at one way of doing StarCraft AIs by looking at the images or generating images from the maps and then using like image analysis to kind of analyze the actual image map of StarCraft and build AIs to try and beat that using neural networks. So I've got really motivated by that. But I've taken a slightly different approach and looking at the actual numerics in the scores of being able to drive a neural network. For example, how many units you've got, how many resources you've collected, what your resource gathering rate is, what the game time is, and see if I can use those numeric values in a neural network. And then also looking at genetic algorithms for evolving build orders.
Cool. Sounds really interesting and very advanced, I have to say. So go ahead, dive in, and show us what cool things you've made using StarCraft 2 in Python.
Great, yeah, thank you very much. So in my session, I'm going to talk about evolutionary learning versus the Zerg, and I'm going to be looking at training and evolving StarCraft 2 AIs using Python. So a bit about myself. My name's Alan Smith. I describe myself as a developer, trainer, mentor, and evangelist. I deliver a lot of training courses. I record Pluralsight courses. I love working with new technologies. So I started working with Microsoft Azure in the very early days, and I kind of saw that AI and machine learning, especially in the Microsoft sphere, is going to be the next big thing. So for about a year and a bit, I've been looking at the AI technologies, working a lot with cognitive services and a lot of the other services we've got, and also learning Python and looking at working with AI in Python. I work for a company called Active Solution based in Stockholm, Sweden. I'm an Azure MVP, and I'm involved with a lot of community work. So I've been involved with the Cloud Burst conference and the AI Burst conference that we've held in Stockholm, and I used to go around and speak at lots of conferences. Unfortunately, nowadays I'm not doing that so much, but doing many virtual presentations now. So my YouTube channel, I've got some videos up there. I've been mostly looking at custom vision and the custom vision service. So feel free to check out the Cloudcast's YouTube channel. There is going to be some mathematical content in this session. There's no avoiding it when we're talking about neural networks and neurons and how we're going to be calculating these various values. So you have been warned. So what I'm going to be looking at is working with StarCraft 2, a bit of an overview of StarCraft 2, and then also using the API to program and programmatically act as a player in StarCraft 2. We'll then take a look at genetic algorithms and how they can be applied to generate the build orders that we've got in StarCraft. We'll take a brief look at Q-learning. I haven't actually built any demos on Q-learning, and I decided to focus more on deep learning rather than Q-learning, using neural networks to actually drive the mechanics in StarCraft. But I'll explain my theories for that as we go through the session. So my session is very heavily inspired by a guy called, he's not called Centdex, but his YouTube channel is called Centdex. And he's done a series of really great webcasts where he was looking at working with StarCraft and building AIs on StarCraft. And what he'd chosen to do is to look at the images, which you can see there. He's basically generating an image from the map, the positions of all of the units, and using image processing neural networks, CNNs, to be able to actually drive and decide, what the best strategy in the game is based on the actual input image. So I was really motivated by that, and I've chosen to take a slightly different approach, but really a lot of the code and a lot of the way that I'm driving the game and programming against the game is really taken from his stuff on YouTube. So I definitely recommend checking those out. He provides a great overview of what he's doing. There's probably about 12 webcasts on that. Also, the Alpha Star, it really fascinates me, the work that this team is putting into working with neural networks. You know, they've got a team with loads of people with PhDs on that, and you know, really heavy computing with lots of GPUs. And what I wanted to do is, you know, can you try this at home? Can you do this without a PhD and maybe without a GPU? And can, you know, just a few hundred lines of Python actually start to generate something that can learn a bit about the mechanics of working and playing StarCraft? So, if you've never played StarCraft before, I'm going to go through just a StarCraft 101, just look at the basics. So you've basically got these three races within StarCraft. There's the Protoss, the Terran, and the Zerg. And they all have slightly different properties. And just for the ease of use, I've chosen to actually develop the AIs to work with the Protoss race. And the opponent, I've chosen to always be the Zerg, just to give some consistency. We always play the same opponent, so the algorithms can basically learn the best way to be able to beat that particular opponent. And it's a real-time strategy game. There's structures you can create and there's units you can create. So start off, if you're you know, playing, you can generate this this home base, which is called a nexus. You get one of these at the beginning of the game, and this is a drop-off point for minerals. You can also generate a unit which is called a probe, and this thing will basically go out and collect some minerals, bring them back to the nexus, and your mineral count will build up. And as you get minerals, you can start to generate additional structures and additional units. So you can generate pylons, which allow you to have a larger population. And then eventually, once you've generated more structures, you can start to generate the fighting units. So there's a kind of a strategy over, you know, should I create a pylon or should I create a probe? And when should I start creating the zealots and the stalkers? And that's basically called the build order, which we're going to look at solving using genetic algorithms. So there's a really complex build tree in StarCraft. This is for Protoss, basically showing the order of all of the units that you can create, the different units and what they're strong and what their strengths and weaknesses are for the other players. So good StarCraft players will basically memorize this, and I basically use this as a strategy for being able to build up the units and the unit trees. Several strategies you can have. You can play very aggressive, you build lots of fighting units and go and kill the enemy as quickly as possible. You can be greedy and you can basically build a productive economy and build up as many resources as you can, or you can have a balanced strategy. And generally, these strategies like aggressive will beat greedy, greedy will beat balance, balance will beat aggressive. So there's a lot of strategy over, you know, decisions over which strategy you should choose. And oh yeah. On to the actual management of the units. StarCraft players will talk about macro and micro management. Macro management is really sort of governing the decisions we take in the overall strategy of the game. Should we gather minerals? Should we build a gateway, build a zealot? And, you know, what units should we build? What's our build order going to be? The micromanagement is really taking the units and positioning them into certain positions as you're attacking to be able to do a much better battle strategy. So what I've chosen to do is to use the machine learning algorithms for the macro management. And the micromanagement, I've just basically hard-coded rules. So you basically go and attack the nearest unit, and that is hard-coded in Python. So I didn't want to spend a lot of time with the AIs trying to learn all of the various different micromanagement operations. There is also on YouTube a great series of lectures from UC Berkeley on game theory with applications to StarCraft. So you can go in and check that out if you want to get more info on the actual theory for StarCraft. So in order to program against StarCraft in Python, I'm using this SC2 library. Now, unfortunately, this is now deprecated, but there are other branches which are evolving. So I did have to make some modifications to this actual build to get it to work as new versions of StarCraft come out. You need to, you know, make slight changes in the actual source code there. But basically, creating a simple bot in this will basically generate a bot that will do a rush strategy on the enemy. So you basically generate a class which derives from bot AI, and then this method here, the async def on step, will basically get called every sort of frame within the game. So this method is going to get called hundreds of times. If the iteration is greater than 0, we're going to basically set the target to the enemy start location, and then for all of the workers, we're basically iterating through the workers and basically sending them to attack the enemy base. So this isn't really a great strategy, but it just basically shows how you can build a very quick strategy as a bot. And you can either hard code all of these rules, or you can use some form of AI to basically take in and make decisions. And this is really sort of how I'm basing my code. Running a game, we basically select the map that we're going to run on, we select the race that we're going to play, and we select the actual bots that we're going to play, and that is the class, an instance of this class that I've defined here. And then we choose an opponent. So here I'm choosing that the computer is going to play with a race of Zerg, and the difficulty is going to be medium. And you can see that I've got all of the other difficulties here, so I can comment in and comment out the different difficulties and test the AI against different strategies. Real time is set to false, which means the game is going to run really, really quickly. So a 10-minute game will run in about 2 or 3 minutes, which is really good when you want to run a large number of games to be able to evolve an AI strategy. Set real time to true and it will run in real time. So a 10-minute game will take 10 minutes. Okay, building units, you've got sort of basic code to be able to actually generate these various units. You can perform checks, can I afford to build this unit? If we can, then we'll call nexus.train probe, and it will basically build one of these probes. And that's basically emulating the mouse clicks that you would do in the game to train those particular units. So evolving build orders, what we're going to look at here is how we can use a genetic algorithm to be able to evolve a particular build order for being able to actually start to play at StarCraft. So a bit about genetic algorithms. It's basically an algorithm, I think they were developed around about the 70s to be able to evolve and basically follow the way that a population will, in an environment, basically evolve. And in nature, this takes hundreds of thousands of years for populations to evolve in a particular environment. But we attempt to do this over a number of generations very quickly by using a computer algorithm. So we start out with an initial population, which may contain, say, 10 or 50 or 100 of these actual units, which are all basically usually randomly generated with slightly different configurations, and the configurations are generated at random. We then have to find out a way of being able to evaluate this initial population and find out of these, say, 50, I've got 5 in this example, out of these population of 5, which is going to perform the best and which is going to be second best and third best and which is going to be worst and so on. Once we've evaluated, and this is usually running a simulation in an environment, we can basically perform the selection stage. We're going to say that the red one and the orange one have performed best, so we'll select the red one and the orange one, and from those we'll perform a process called crossover. And this is naturally what happens during the breeding process. The child will get genes from the mother and genes from the father, and those will basically be merged together to be able to generate somebody containing those genes. So by taking the most successful genes and using that for crossover, we get a new set of population that inherits hopefully from more successful genes. We then perform something called mutation. We randomly change or flip or modify some of these values just so that we can actually, hopefully improve the generation. Sometimes these will have a negative effect, very often, but sometimes this mutation will have a positive effect, which means that the next generation is hopefully going to be more successful. And then we go around the loop again. We evaluate, we select, we cross over and mutate, and we go round a number of generations, hopefully seeing an improvement in the performance of these actual population members in the environment. So how does this relate to StarCraft? We basically generate 10 random build orders. And the build order is saying, okay, let's build a probe, build a pylon, build a nexus, build a probe, build a probe, build a probe. And we generate 10 of these at random. We then simulate by playing a game of StarCraft using each one of these 10 build orders. And we need some way of evaluating and deciding which is the most successful. So one of the ways I've looked at doing this is, at the end of, a certain amount of time, maybe 10 minutes, I would, the most successful gene will be the one that has the highest number of resources gathered per minute. So that's a statistic that you can pull out of the game. So once you've done that, you can basically order these build orders into the build order that gives you the highest rate of mineral gathering per minute. You can then perform the selection and say, okay, let's select the genes with the highest mineral gathering rate, perform the crossover by combining these build orders, making a few random changes in the build orders, and then going back to the evaluation stage. So this is basically what a chromosome will look like. This is sort of one of these that I've copy-pasted out of the game. So it's saying build probe, build probe, build probe, build a simulator, build stalker. This one's building some military units as well. So that's going to be what we're evaluating. It's just basically an array of these actual build events. And when we're simulating this, this is kind of what a build order will look like. And this is the best build order from the first generation. As we go into the second generation, you can see that we have made a modification. So this is the in the second generation, the first build order, we decided to flip this nexus for a probe, and that gave us an improvement in the performance. And here we've made some other changes in the build order. We decided to build a probe instead of building a pylon, and then that allowed us to build an additional pylon at the end. And as we go down through the generations, we did get stuck here, where we got basically several generations with exactly the same build order, but then we did get a slight improvement here and a slight improvement here by starting out by building a unit at the beginning. So these build orders will hopefully evolve, and it will hopefully generate the build orders. This is one of the optimal build orders that I got after doing maybe 24 hours of evolution with creating, and this is just one for generating resources. So this is showing the actual statistics that came. Along the bottom of the graph, we can see the generations. So this is generation 1, then 2, 3, 4, 5. And we've got the average score, which is shown in blue, and the maximum score, which is shown in orange. And this is the actual mineral gathering rates. So this is fairly typical of a genetic algorithm, how it will evolve in an environment. We get kind of a steady increase, both in the maximum and the average score of all of the members of the generation. That tends to increase. And then we get this thing where it basically tends to level off. We're running more and more generations, and we're not getting any improvements there. This could be that we've got the optimal solution, or it could be that we've kind of stuck, because we're generating the genes randomly. You can get, some gene combinations aren't never going to evolve to a higher strategy. So that's basically showing the results from one of the tests. This is where I was showing for maximum military evolution. Maximum 1 came out there doing fairly well, but as we evolved over the generations, we were able to build more military units during the allotted game time by evolving that. This technique has been used a while ago. They were talking about somebody who basically built a project that was called Evolution Chamber, which was able to come up with an unbeatable build order in StarCraft 2. And there's a lot of talk in the StarCraft community about this actual build order that had been developed. There's a Wired article on there from about 10 years ago that was talking about that. So there are scenarios where this these kinds of techniques can basically generate build orders that can start to challenge human players. Okay, I'm going to demo this and look at genetic algorithm versus the Zerg, and we'll start out with this Visual Studio project here. I'll just zoom in a bit on the code and run through a bit about the basics of how this works. So what I've got is this code here. Normally when I'm running these, the StarCraft GA will basically start out with a class called a genetic algorithm, and it will basically run through the actual evolution of this. Now, it can take about 24 hours for this actually to evolve, running through all of the generations. And what it will do is it basically saves the statistics at the end of the game. So this code here, play with gene, what I'm doing is I'm basically taking this statistic, this gene, which is evolved military, and this has evolved from one of these 24-hour simulations. So this is kind of like the one we saw on the slide deck. And what I'm doing is I'm basically generating a new instance of the GA bot, which is the class, which is going to run through the genes. And you can see here we've got this statement here where it's running through the genes. If it's build probe, then we're going to attempt to build a probe, a zealot, a stalker, and so on, by calling into the StarCraft API. And I'm basically setting the chromosome of the bot to this array that I've developed here. The max game time is going to be what's that? Yeah, this is going to be 10 minutes. Max game time is going to be an hour, but I've set this bot attack at to be 10 minutes. So after 600 seconds, 10 minutes, we're just going to send all of the military units into the enemy base and attack the enemy base. And here we're spinning up the game. So I'll actually run it on the medium level to start off with. It usually wins on medium, and I'm going to save that, and I'll just run this. I've got real time set to false, so I'll just start this running. So what we should see popping up is the actual Python application itself, which is the console. That then, when I'm calling the code here, run game, is going to spin up an instance of StarCraft. It's going to take a few seconds for StarCraft to load. and that's loading up with that particular map. And hopefully, oh yeah, so we're in the game now, and once the game kicks off, we'll see the actual build order coming here. It's build pro, build pro, build pro, build a simulator. We can see the game clock. We're up to 1 minute now, 1.5 minutes, coming up to 2 minutes, and we should hopefully start to bring in the military units. So we've got our simulator here, and hopefully the military units will be coming along fairly soon. Yeah, we've got some already. This here is saying the number of military units. It might be a bit difficult to see, but we've got 7 military units, 8, 9 coming here, and these are basically starting to build up here. They are programmed. If somebody, like is happening now, somebody comes in and tries to attack the enemy base, then we will basically send the military units in to defend that enemy base. So this is the micromanagement that I have basically hard-coded to send these in to just attack any enemy units that are detected. But the build order is basically being created by the AI. This is what's basically governing the resources that we are creating. So we're coming up to about 9 minutes. When it gets to 10 minutes, we should go and attack the enemy base, which is down here somewhere. So we'll just zoom in on these units as that starts to happen. So yeah, we should be going about now. So you can see there's this huge attack now going in. And if I go down to the enemy base, we'll see these guys come in. There it is. And we're just doing this mad rush now with all of the enemy units going in and trying to destroy this enemy base. Hopefully this one is going to be successful. Yeah, so the AI wants to surrender now, so we'll allow it to surrender, and we won that game. So I'm just going to test this now. I'm just going to drop in the comment there and just drop it onto the hard difficulty. I'm going to save that and just try running it on hard. Okay, it's given us, it randomly picks the base, so it's given this one at the bottom right instead of a top left here. And I'm expecting this AI to get slaughtered, which will basically expose one of the main weakness of choosing this particular strategy for evolving the AIs. So basically, the genetic algorithm it's just got this, pre-built build order. So it's going to go through, it's going to build all of these units, create all of the units, irrespective of what the enemy does. So if the enemy comes in and suddenly does an attack, we probably need to build, more of these resource gathering units if it destroys all our resource gathering capabilities. But we're not actually looking at any of the inputs here. You can see the enemy is attacking now. It's trying to destroy our units, but we just keep going through this build order, which was trained on the medium level. So it really hasn't evolved in the environment where it's playing against hard enemies. So fairly quickly, I think it's going to get all of the units destroyed. I don't think it's got much of a chance now. We're down to, 1 military unit, and the bases are getting slaughtered. And it's attempting to build these resource units. It's just building more probes. So this one isn't going to be too successful. I'll end this now and just save you seeing the pain of that one getting defeated. Okay, now I did consider looking at using Q-learning, which is a technique that can be used for sort of solving these processes. This is kind of a ice hole challenge. It's one of the applications that we've got in the AI gym, and the idea is that based on the square that we're in and based on the move that we can make, this is kind of simulating, you're a speaker at a conference and you need to get to the sauna. It must be a conference in Finland. If you want to go in this direction, there's only a 33% chance that you will go in that direction. You could go up or you could go down. So the idea is try to use AI to determine the best method for being able to get through this actual ice maze and make it to the sauna. And you can use a Bellman equation for this, but generally the idea of this is that for every square that you're in, there'll be a certain action that you can take that will hopefully transition you to a more successful state. And then based on the value of being in a particular state, this one probably has the highest value because then you can transition to getting to the sauna. You know, the probability of being able to transition to this state is something that can be calculated using the Bellman equation. And you could apply this to StarCraft. You could have, you know, based on the game time and the mineral gathering rate, you could have statistics on whether it's better to build probes or whether it's better to build military units. And that would basically form something called a Q table. Now, I'm going to whiz through this because I haven't really implemented this in the as an actual implementation. But as these get more complex, as we have more inputs and more outputs, the Q table basically gets a larger number of dimensions. And what this means is that as we're trying to calculate what the best action is, there's going to be you know, thousands and thousands of these you know, possible combinations of inputs and outputs, depending on the granularity and the number of dimensions that we're running. So if we're looking at you know, various scenarios, if you've got, say, 5 dimensions, 8 actions, and a granularity of 10, there's going to be something like 3.2 billion different values. And being able to evaluate and figure out all of the values in these Q tables is going to be very challenging. You may randomly end up in one of these you know, squares that says, okay, the most logical thing to do is to attack the enemy base, because it's never been trained. We've never experienced that before. So because of that, I didn't really implement the Q learning as a StarCraft one. What I kind of figured is that we don't really need a table of elements. We really want a graph where we can have a multi-dimensional graph with a formula. And this mathematical formula is going to tell us whether the actual probability of building probes based on various input things. So here I've got the game time, how far we have progressed through the game, and along the bottom I've got the resource gathering rate. So at the beginning of the game, when the game time is 0 and the resource gathering rate is 0, it's highly probable that we want to build more probes. So this area at the top of the graph is saying build probes. As we get towards the end of the game, and as we have a high resource gathering rate, there's less of an example to build probes. So this, having an actual formula, basically means that we don't have the problem of these discrete values. So this is where deep learning comes in. We're really going to try and derive an actual formula. And this is where the math starts to come in. You could say that x equals to RA plus GB plus TC plus MD, and x is whether you should build resources. And you've got the mineral gathering rate, gas gathering rate, game time, and military force. And you really need to figure out these probabilities and set these various values. Now, if you're into machine learning and neural networks, basically a neuron can do that type of calculation for us. We can feed in these various values, we can set various weights in the neuron. And through the formula that we've got within a neural network, we can basically calculate the probability for taking a certain action. So examples of this, just putting in some numbers in and showing the formula, we can do our actual calculation, we can use a sigmoid function, and we can basically figure out that the probability with these inputs and these weights is going to be 0.94, which is going to be 94%, which is fairly close to 100%. So we should probably take that particular action. So if we connect a bunch of these together, we get something called a neural network, where we can feed in the inputs from the game values, and our outputs are going to be whether we should build resources and whether we should build military and so on. We can think of these intermediary layers as maybe being something like the mineral maturity, gas maturity, military maturity, how much resources we've got based on the particular game time. So the hidden layers allow us to do more complex calculations and generate more complex algorithms. So for the next demo, we're going to be using TensorFlow, and we're going to be using Keras, which is a wrapper around TensorFlow that allows us to program fairly easily using Python. Now, typically with neural networks, the way that we program against a neural network is through backpropagation and providing test data. So this is a number 2. I know that this is a number 2. So what I can do is I can train my neural network by setting the weights and setting the biases, so that over the actual training iterations, it will, classify this particular image as a 2. However, we don't really know this for StarCraft. We don't have our actual output data. We want to do evolutionary learning. So what we're going to be doing is using the same concept as we did with build orders. Instead of generating an array of strings, we generate an array of floating point numbers, and we set the actual weights in the neural network based on these numbers. We can then take the genetic algorithm, we can evolve through the neural network and basically generate the appropriate evolution and performance stats. The crossbreeding is going to look slightly different. Here we're basically randomly selecting from the self gene or the partner gene to be able to perform the crossover action. For the mutation based on a mutation factor, we're basically flipping one of the actual genes. We're setting it to a new random value, and we do this in a small number of the gene values. So this is showing the evolution that we got from 180 seconds of resource gathering, optimizing the resource gathering. And this is the actual output graph that was generated from the neural network. So what I did is I trained the neural network for resource gathering over probably about what was it, about 11 generations until I'd kind of reached that flat level in the graph. And this basically gave this output. And what I've done here is basically set in the gathering rate and the game time into the neural network. And this is the output from the neural network, which is giving us this nice, smooth graph, showing us, when we should do resources. So that graph I showed earlier, we had actually evolved that graph using genetic algorithms and neural networks. So I'm going to hop into a demo and show how this code works. This is slightly different in that what the actual chromosome that we're using is going to be an array of integers. So we're basically generating the genes as being an array of floating point numbers. The gene length is going to be dependent on the actual neural network. So this is the model that I've created. It's using Keras, and I don't have the code that created the model somewhere. I think it might be in here. Yeah, so what I'm doing is I'm generating a fairly simple model. This is a sequential model. I'm generating this with the two inputs, and then it's got this middle layer that has 3 inputs and the output with 2 outputs there. And what we're doing is a genetic algorithm is just basically going through the evolution process. So we start this off with a certain number of genes, and then we're going to go through our various operations. In the selection, we're just going to be doing a sort on this. So what we're doing is we're basically sorting the list based on the actual score, which is going to be the amount of resource gathering, and that's going to give us the list in descending order. So we just basically reverse that list. Then we can go through the other options that I've shown on the slides, the crossbreeding and the mutating there. Now again, this will probably take about 24 hours to evolve. So in Play Max Zealots, what I'm doing is setting the actual weights of the neural network to actual values that I've got from a previous evolution. So these values are the weights in a neural network from the best performer in the the latest generation when I've run through one of those simulations. So we generate our new neural network. We then basically set the weights within the neural network by calling set weights, and then we run through the same simulation process. We've got this bot which is going to be using the neural network to actually determine whether it's going to build resources or whether it's going to build military. So this one bot is going to be the Max Zealots bot, so we can have a look at that, I think. Yeah, so this is fairly straightforward. What we're doing is we're basically calling predict on the model. We set the inputs of the model we call predict, and then if the first output here is greater than 0.25, we're going to gather minerals. If output 1 is greater than 0.25, we're going to build zealots. So it's fairly straightforward just to take that decision based on the output of the neural network. So I'm going to run this. I think I was playing on the medium level here. And what this is hopefully going to do So this is also showing the neural network. What I'm doing is basically drawing this graphically. So we can see this is the game time and this is the number of units. And what we can see is the actual neurons firing and basically triggering the outputs, whether we should build resources or whether we should build military, as we're actually running through the simulation. So what this is doing is it's basically taking various information from the game, the actual scores from the game, feeding it into this neural network. One of the challenges is that this really slows down the game as we actually see the neural network firing. So we will probably see the game time start to degrade as we actually run through this particular simulation. So it's not running as fast as it should do. So in order to get the game completed, what I'm going to do is just exit from here. I'm going to comment out the visualization without visualizing. And what that's hopefully going to do is run through the game a lot faster. And hopefully we'll basically see if this is going to give us a victory on it. Go and kill that instance of StarCraft because that's not doing anything. It's this one that's active. Okay, so this is started building here. This is only going to build zealots, which is the basic units. So the success criteria is how many of these zealots we can build, these enemy units. And we've basically generated about 4 of them. I'm just going to go here and just press F2 and just move all of the enemy units over here, because we should have the option of being able to attack the enemy base with these units that are built up. I think it maybe needs about 30 units here. But the macro strategy here of generating the actual build order, choosing what to build, is governed by the neural network here. So that's basically got us up to about 33 units. So the enemy base is down here. I'm just going to see if we can send in these units. We're now up to 37 of these. So maybe we can get a rush strategy to work on this particular map. So let's see if we can take that out. That was quite successful. And let's see if we can take this out. The problem with the zealots, these little units, is they can't really attack air units. So once any kind of air units has been built, then it's pretty much game over for this. But we still seem to be producing units. Hopefully we might be able to get a win here. Yeah, so this one wishes to surrender, so I'm going to accept that, and we've got a good game. Cool. So just some reflections on what I've been doing with this. It is incredibly time consuming. A simulation is taking typically about 24 hours to run. And that's the challenge, and that's the kind of thing that slows you down. It's fairly easy to write the code. It's fairly easy to get the things working. But, leaving your PC running 24 hours pretty much every night and then making a few tweaks to the game and leaving it running. It took several weeks to actually, get this working and get all of the evolutions working and be able to make the changes in the actual game to actually get some good evolution going. So just to summarize and give you some resources that you can check out if you want to explore this type of thing. Again, I'm going to recommend Sendex's channel. There's tons of stuff on working with Python and working with AI. If you're a .NET developer like I am, pretty much this is how I've learned Python. I didn't really learn Python before getting into machine learning. I learned it as I went on. I'm not the greatest, I'm not really that great at programming in Python, but it's fairly easy to learn. It's a fairly logical language, and there's some really good learning resources out there. Sendex as well, he's done some stuff on Python Plays GTA, which is definitely worth checking out. Code Bullet, Australian, I think he's an Australian student who does loads of evolutionary AI. I teach AI to kids. I've been teaching AI to kids at some of the code camps. Unfortunately, I can't show any of Code Bullet's videos there because he curses like a sailor, unfortunately. So there is some ripe language in these, but they're definitely worth checking out. They're very amusing, and he chooses loads and loads of different diverse challenges and then builds AIs to be able to evolve. And he's published quite a lot of code on GitHub. So this is a really nice one, looking at using a genetic algorithm to be able to get these dots to move to a particular goal and be able to navigate past obstacles. And I've played around with this code, which is written in Java, and it's a nice way to get into learning about evolutionary programming and genetic algorithms. I really like Jabril's as well. He does a lot of game development. He also focuses quite a few of his webcasts on looking at AI. And he did a series on forest AI webcasts. So he's really good at explaining how AI works. And I really like the way that he presents and the way that he runs through. And he talks about, his learning process. When he starts off on the first webcast, he's a beginner and he's just learning the basics. And he sort of talks through the whole learning process of, how you get your head around these algorithms, how you develop your skills, and he's really entertaining to watch as well. And then, of course, you've probably seen this one, 3 Blue, 1 Brown. He provides lots of webcasts on maps. He uses these beautiful animations, which are developed in something called Manim, which is available on GitHub if you want to play around with that. And he's given the best explanation I've ever seen on looking at how neural networks work and how backpropagation works. And everything's really animated really nicely using these types of graphics. There's a lot of mathematical content on there if you want to learn the maths, but there are a few really good ones looking at machine learning and artificial intelligence and so on. Of course, Tess Ferendez, who's been presenting here as well. I really like her presentations. Unfortunately, she doesn't have her own YouTube channel, but searching on YouTube, there's some great sessions that she has presented as well. So thanks very much for listening. My name's Alan Smith. I work for Active Solution based in Stockholm. Feel free to contact me and feel free to check out my YouTube channel. Ask any questions in the chat if you've got any questions. Thanks very much for listening.
Awesome. I like that so much, dude. It's really great to see someone hack a game like that. It's really inspiring. So, one question that I have is how many games does it actually play before it gets anywhere?
Yeah, I mean, we can go back and look at the I think I'll bring up the statistics there on the genetic algorithm, which I kind of thought showed the most interesting. So you can see the generations. I think I was running about 20 games in each generation here. So basically that's going to be, yeah. So here it's getting up to about 200 games, maybe about 400 games around here. Yeah, so probably about 400 games if there's 20 per generation. Then it kind of started to level off here. And I guess it would depend because mineral gathering is fairly straightforward. It would really depend on the complexity of the problem. In this one, it kind of leveled off at around about 20 as well, 20 generations. You can, change the number of members in each population you have in the generations as well. But then again, setting it to 50 members in a generation is going to take a long time for that to evolve, and it's maybe going to take 48 hours instead of 24 hours to reach this particular point in time.
Cool.
That's amazing. Yeah, such a good talk. It was one of those ones where I was sitting in like suspense when you changed it to like the hard level mode, and I was like, oh my god, what's going to happen? It's a really good stuff. Thank you so much for sharing. Quick question on the approach and like technique you used with genetic algorithms, but then with the neural networks as well. Can that be applied to other games? And do you just need to then choose sort of like rewards and actions in some senses?
Yeah. I mean, a good example is the Global Azure racing game. We had the Global AI Bootcamp, and for a number of years at the Global Azure Bootcamp, I've had this racing game where we're using Azure Storage and Azure Service Bus like for the back end of this like 3D driving game. And then I saw what the guys are doing with the Global AI Bootcamp, Henk and Willem, and thought, we've got to take this racing game and do some AI with it. And I'd already seen Centdex doing his stuff with GTA. So I basically worked with a 2D simulation of just getting the algorithm to work with the 2D driving game, and then ported it into the 3D driving game. And it was really cool just to see it evolve and basically learn how to drive around a track. And looking at the scores, it was basically beating the human players towards the end of the game. It was getting about 1 or 2 seconds faster lap times than human players, because it would just basically evolve doing a perfect lap. And that's pretty much very similar. The neural network basically had these like 5 inputs. So you had the distance forwards, and then these kind of distance sensors off at 45 degrees and 90 degrees. And so it would basically detect the distance to the edges of the track, and it used those as the input to the neural network, and the outputs to the neural network was the steering and the throttle and brake. And that, over like 10 generations, it could sometimes evolve to, do a really good lap. So that's interesting to see.
Yeah, no, that's... I know. I literally want to just jump off here and then find a game that I'm really in love with and just make it completely AI related now. So yeah, there we go. I've lost all my evenings. Thanks a lot, Alan.
It is a time sink. It will consume a lot of your free time, but it's good fun.
Yeah, I guess if you're done playing the game yourself, you could actually let the computer fix it for you, so you've got time to code. So what would it actually take to get started with this? I imagine that, so in the case of StarCraft 2, you have a specialized API that actually allows you to automate the game.
There's a number of APIs.
Is that required for every game, or are there any other techniques that I can apply to this to get data out of the game?
Yeah, I mean, having the source code to the game, or having some API that allows you to programmatically program the game is really going to be a big help. I did look at Plants vs Zombies as well, but the challenge there was you had to do all of the image analysis to look at what was happening in the imaging, and then actually send mouse clicks into a simulator to actually plant the plants and actually perform the game. So actually, the actual interface onto the game was a real challenge. But the stuff that Code Bullet does and the stuff that he's put on GitHub, he basically writes his own game and then writes the AI to be able to beat the game as well. So he's done some incredible work with that, and some of his stuff's available on GitHub, so you can play around with those. But really, either getting a sample game, which is what we've done. The global AI bootcamp, the Racing Lab, it was based on the XNA sample. I don't know if you remember XNA. It's a gaming thing that Microsoft had probably about 15 years ago. And the racing game was actually the source. They just basically had the source code of that sample game, which I then modified, and you could actually program and build the code into the game itself. Yeah. There's a good webcast as well. The King, who developed Candy Crush Saga, they were talking about how they use genetic algorithms in Candy Crush Saga to test levels. So when they develop a new level, the level testers build a new level, they send it to the AI, and the AI will basically figure out how difficult is the level, how challenging is the level, by learning how to play it. So there's obviously a lot of money to be made as well if you're working on one of these online games, making it addictive and playable, and putting the right balance of a level into right balance of difficulty into one of these levels is going to be good to give you really good playability.
How cool. So how would you use it in real life then? So I can imagine this works for games because that's pretty obvious in a controlled environment. Would this also work on real life things, and where would you use this?
Yeah, I mean, the thing I like about the genetic algorithm is it can solve so many different problems. One of them is like the old traveling salesman problem. Kind of not relevant now, but you've got a number of cities that you've got to travel around. You've got to find the quickest path between these cities. Starting at your city, visiting these 20 or 50 cities, and getting back to your starting location. Now, you can write an algorithm that specifically solves the traveling salesman problem. Or you could just use a genetic algorithm and generate 20 different routes, look at the actual distance in the routes, pick the top 2 routes, and use those with crossover and then mutation, and go on to the next generation. And the genetic algorithm can fairly quickly come up with a very good solution. Maybe not the optimal solution, but a very quick solution to that particular problem. And it's really two things that you need. Firstly, it's a problem where you don't have the test data. You've kind of got, instead of the test data, you've got this simulation environment. So you need a simulation environment that you can run and test these generations in. So a game is good because that is a simulated environment. So something you can actually simulate and actually test these algorithms. Obviously, it's not going to be too great for Tesla to use this for their cars. Stick 100 Teslas out in the car park and they can drive around and crash into each other. And we'll take the best 2 and send 100 new Teslas out the next day and see what they do. So without the simulated environment, it's challenging to do that.
Cool. So I was thinking, so this reinforcement learning thing, would that also work for very simple problems? And I can imagine StarCraft 2 is very hard to solve, and also driving a car is very hard to solve. But how would you use this in a very simple case? Let's say a very simple game like chess or something like that.
Yeah, there's a great book that where they did it with, not with chess. Chess is pretty complex. They did it with drafts or checkers. And the book, I think it's called something like Blondie 24, and it was written about 10 or 15 years ago. And it was a couple of researchers who were basically looking at using a genetic algorithm and a neural network to be able to come up with the best strategy for playing checkers. And what they did was they basically played it online on, I think it was one of these like online checkers games, and they actually got really high up in one of the leagues, evolving this checkers game. And the book that they published was really good. It basically went into lots of details about how they developed it, how they'd evolved it, and I think they spent about 9 months evolving this algorithm on a really, I think it was in the 90s sometime. PCs weren't that fast in the 90s. There's no GPUs. So they're spending so long just basically evolving these algorithms to be able to play checkers. So yeah, it can be done like that as well. Then there's many simple problems that you can look at. I think there's an application or a project called, is it AI Gym? Where you've got all of these like simulations that uses, I think, Box 3D physics engine. So you do stuff like there's a pole balancing one where there's a cart and there's a pole on the cart, and you've got to basically move the cart to basically keep the pole balanced. And there's another one where there's kind of like a hill climb, and you've got to move a car backwards and forwards to get up the hill. And those are like really sort of simple problems that you can look at building Q learning and genetic algorithms and just write code to be able to run against those simulated environments there. And then you've got more complex ones, like there's a walker, so a biped with 2 legs, and you've got to evolve the actual walker to be able to learn how to walk and things like that. So that's really good for many simulated environments for being able to play around with AI. I think they've also got the ice hole challenge thing that I did. I think that's called Grid World. Their actual simulation of that you can run.
Yeah, sounds really cool. So our evenings are going away. We're going to try and beat your bot actually in StarCraft 2, I think. And with that, I'd like to thank you for your time and your awesome presentation. And so we're going over for a short break. I'll be off for a few hours. And Sammy will replace me, I think, in the next hour. So with that, thank you very much. And
Thanks.
Be right back.
Yeah. Enjoy the rest of your day. Thank you.
Thanks.